All right, so what we're going to do next is just like we did for electric fields, we're now going to use BioSavat to develop approaches for things starting with currents and then going into different shapes to get magnetic fields. So, naturally, in the real world, we typically don't observe electrons by themselves unless you're doing a precision measurements is an unusual measurement. So we need to have some way to sustain charges in constant movement, which is what a current is. So current is sustained electron or other charge movement. Okay, so what we're going to do is we're going to see how this is done and then also how this relates to what we know about magnetic fields. So, if we have a wire, delta L, and cross-sectional area, A, so this is essentially the volume of the wire, and there are N moving charges per volume in A delta L. So we put this together and we get N A delta L. So this is the moving charges in this particular volume of wire. We assume each moving charge is producing about the same magnetic field at the point of measurement, which is reasonable. So delta B is equal to mu naught over 4 pi I delta L cross R hat over R squared. Okay, so let's break this equation down. So in terms of our previous expression where we had Q times the velocity, we can see that this would be embedded in this expression right here, where a current is going to account for all of the charges moving at their drift speed. So let's look at what delta L is. So delta L is a vector with magnitude delta L, which is the length of the wire, and the vector delta L points in the direction of conventional current. And so you might be wondering, well, would this work for electrons as well? And of course it would, because we've already discussed how when you've got an electron, then you have a negative charge also moving the opposite direction. So you simply know that we're going to calculate it as though it is moving the opposite direction. All of the actual physics principles work out. And then if you're asked what direction the electron current is going, just say the reverse. So remember, I had nothing to do with this decision in physics. It was made long before I was born. All right, so delta B is equal to mu naught over 4 pi I delta L cross r hat over r squared. And really this right here is just mu naught over 4 pi q v cross r hat. Well, this is the sum of all of these, so we see that we have units of Coulomb meters per second, which gives us the Tesla we're looking for. All right, so moving on. 17.7. The magnetic field of a long wire. So just like we did in chapter 15 for electric fields, we're going to take a divide and conquer approach to deriving different fields. And so the steps for that are cut up current distributions into pieces. And then we're going to draw the contribution of each magnetic field for one piece. 2, write delta B for one piece. Step 3, add them up. And step 4, check the result. So this is why we're spending the time to learn this process, is it's really not just a useful process for deriving electric fields. This is how a lot of analytical expressions are derived, and it's something that if any of you go into a research track in your fields, you may use this type of approach to break something down into smaller, more manageable pieces. All right, so we're going to take this approach with a long, straight wire. Very long, very, very long. All right, so we would have some length L. And we're going to put the origin right at the middle. And so we would have little chunks of this wire, delta L. Let's say we're going to observe right here. So this is our R vector. Or this is R hat. And remember, the magnetic field is perpendicular. So we would have our Z, or R is equal to, I can't read my writing. R is equal to x squared plus y squared. So this is our delta B contribution. All right, so this is our picture for this setup. By the way, there is some excellent 3D pictures in your book that I recommend looking at, because I do not draw well in 3 dimensions, or really in 2 dimensions for that matter. Drawing is not my strong suit. My husband is the artist in the family. All right, so step 2. We're going to set the origin at the center of the wire. So then R is equal to x minus, or x0, 0, minus 0, y, 0. So we're observing an x. We've got our little delta L here. And so R is equal to x minus y, 0. So far it's looking pretty similar to when we did the electric field. So our magnitude is equal to x squared minus y to the 1/2, which we predicted. And R hat is equal to R over R, which is equal to x minus y 0 over x squared plus y squared. And y is our summation variable. So we can do delta L in terms of y. So delta L is equal to delta y, 0, 1, 0. And delta B is equal to mu naught over 4 pi I delta L cross r hat over x squared plus y squared. And we can go ahead and flesh this out. So, if you recall from just 2 steps ago, delta L is equal to delta y, 0, 1, 0. So we can plug that into our expression, and we get mu naught over 4 pi I delta y, 0, 1, 0 over x squared plus y squared. And we'll do the cross product of that with x minus y, 0 over x squared plus y squared to the 1/2. Now, these are the only two things that are vectors, so I'm just going to pull these out because I don't think you want to carry along all these scalars in front of those vectors. Ugh. So 0, 1, 0 crossed with x minus y, 0. And this is equal to 0, 0 minus x. Feel free to check that on your own. It's a really excellent cross product practice. And what we can see from here is we only need to calculate in z. Okay, so step 3, we're going to add them up. And this is going to be an integral approach. So delta y will go to 0, b mu naught over 4 pi, ix going from y equals minus L over 2 to y equals L over 2, dy x squared plus y squared to the 3/2. This is another one where you need a table. So I will just give you the result. So we have b is equal to mu naught over 4 pi ix y x squared plus y squared solved from y equals plus L over 2 to y equals minus L over 2. And simplifying this further, b equals mu naught over 4 pi ix L over 2 over x squared plus L over 2 quantity squared minus L over 2 x squared root x squared plus L over 2 squared. And this solves to b is equal to mu naught over 4 pi Li over x squared plus L over 2 squared. And when L is much, much larger than x, or x is much, much smaller than L, so a very long wire or a very short wire, b becomes approximately mu naught over 4 pi 2I over x. And we can check the results. So it is right-hand rule consistent. And the units, Tesla meters over amps. Meters, amps, meters equals Tesla. So that works. And then I have another right-hand rule. If you put your thumb in the direction of current and curl your fingers, that is where the magnetic field is. So this is the thumb in conventional current. And if you curl around, that is how the magnetic field goes around that wire.